The software design team designed two separate brackets for this project. Each design was based off of Lockheed Martin provided requirements and were created using two different methods of additive manufacturing design. I'll turn it over to Paul and Drew, who can walk you through the two designs.
In order to perform topology optimization, two things are necessary: software and a model to optimize. On the software side, this design utilized Dassault Systems, SolidWorks, and Topology. Each software platform would serve a specific purpose. SolidWorks was used for CAD design, modeling, and simulations. This was due to its platform maturity and need to establish baseline properties. Topology was used to perform advanced modeling and simulations focusing on additive manufacturing strengths using the CAD models from SolidWorks. What you see on the left of the screen is the design space provided by Lockheed Martin. In the middle of the screen is a simple structure called the conservative bracket design. It fills the build volume specified in the provided drawings from Lockheed Martin and will be used as a guiding example for optimization. It is broken down into three distinct design areas of zones. The major part zones are rocket engine mounts, side frame supports, and a front valve plate. The rocket engine mounts, side frame supports have been sized deliberately to fit the build volume of the EOS M290 machine. In this slide, you see some of the interesting additive manufacturing design features Topology brings to the design process. Lattice infill has been added to the rocket mounts. We found that these lattice additions add very minimal mass but bring a nice increase in stiffness response. The stiffness increase brings better modal responses and an overall increase in safety factor. With more time, we were hoping to physically print and test several components using these technology features. Topology also offers some other unique benefits. It has the ability to slice an object, add custom support material, and directly code into the operating printer machine language. These features would normally be found on another expensive software package, so this could be a huge plus or benefit to Lockheed Martin using Topology. The iterative optimization process continued until model revision number 11, which brought the final design you see here. This model has been tested and lightweighted simultaneously in SolidWorks and Topology. We were able to achieve the goals you see on the screen here. The total assembly mass is now down to 4.93 pounds with a unique part count of just 4 pieces. We were able to reduce the fastener count to join all the components to just 19 fasteners. This brings the achievements of 27% reduction in fastener count, 19% reduction in mass, and 28% reduction in the part count, all from Lockheed's current design.
This is the bracket that was designed generatively in the ANSYS software package. It is a 3-part design consisting of the rocket housing, the side pieces, and the valve plate. The rocket housing weighs approximately 5 pounds. The natural frequency still needs to be tested. 2 side pieces are used in the bracket assembly, each weighing 1 pound with a natural frequency of 145 hertz. The valve plate weighs 1.87 pounds with a natural frequency of 249 hertz. The total weight is approximately 9 pounds with 8 fasteners. The rocket housing is a 1-piece generative design. The focus was on eliminating support material while reducing part count. Most of the recognizable geometries on the rocket housing were spliced into the generative design to allow for ease of printing. Some of these can be seen on the model. A flat base was added where the part would touch the print bed. Gussets were added to ease the transition of the support material onto the organic-looking arms. The large triangle was designed to support the entire upper portion of the rocket housing, while weight relief diamonds were cut, all with printable angles. The bolting locations for the side pieces also had added material that would later be machined off to eliminate support material at that location. Although the rocket housing still has support material when printed, it was reduced dramatically. The side pieces are reversible and the bracket requires 2 of them. They can be printed without any support material and were designed with topology optimization guided method. This method was chosen to ensure that the side pieces adhered to both loading conditions and natural frequency constraints. A design space was created with loading conditions and an FEA analysis removed material that was not necessary. The side pieces were then tested for the natural frequency to determine if the part still met that criteria. Then the process was repeated to reduce weight further. Once all non-essential material was removed, weight relief diamonds were added into the part, and the surface that touched the print bed was angled so it would fit in the available volume of the printer. This bracket meets the design goals by reducing the total unique parts down to 3, while being assembled by just 8 fasteners. Designing with ANSYS allowed me to leverage 2 powerful tools. I was able to design the rocket housing generatively as one part. Using an iterative topology optimization approach, I was able to make the side pieces universal, lightweight, and strong. And you can see just how promising the results are.